Good afternoon. This is Senior Design Team S1 from FIU's BME department. We'll be presenting our project on developing an intraocular phototherapeutic implant for diabetic retinopathy. I'll let Shoshana kick us off with our background and problem statement.
Thank you, Johan. So I'm going to start off by saying that diabetic retinopathy is the fifth leading cause of preventable blindness among diabetic patients, those at the ages of 50 years and older. The problem we have with the current treatment modalities is that they often yield low patient noncompliance and require revisits. So some of those examples would be the anti-VEGF injection, which is injected at the back of the eye to prevent neovascularization. This treatment is continual and indefinite. The panretinal photocoagulation, our next example. This is a laser treatment which can burn and destroy parts of the retina, often risking permanent vision loss. And lastly, the light-emitting contact lenses. The patient often has to replace those time to time, which can risk corneal abrasion and infection. So to mitigate these issues, our goal is to develop a long-lasting phototherapeutic implant to treat diabetic retinopathy. This implant would be inserted in the posterior orbit of the eye to illuminate the retina while the patient is at rest. So from this illumination, we aim to reduce hypoxia, which can prevent retinal neovascularization. I'll now pass it over to Johan, who will start us out with the market requirements of this device.
Thanks, Shoshana. In designing this device, we decided to be intentional with our design choices, so we compiled a list of market requirements and design inputs. However, given the short time frame and scope of this project, we decided to only verify 3 of those. The first of those is that the LED must illuminate when stimulated during the entirety of the patient's rest. To meet this market requirement, we created a design input specifying that we maximize this light dose's effect physiologically by keeping the designed color of our device between 490 nanometers and 530 nanometers in wavelength. This is a range that contains the maximum absorption of the rod cells. Secondly, we decided that the LED must provide low-level illumination. Now, in order to provide a range of photon flux that the device must deliver to the rods, we decided to get a range that was in a scotopic level of photon flux. So we went with 30 photons per square micron per second in order to sufficiently hyperpolarize the rod cells, but stay below photopic vision, which is at around 2,000 photons per square micron per second, so as to avoid stimulating the cones and hyperpolarizing them, further disturbing the patient. Lastly, for safety's sake, we decided to make a marker requirement that the implant must not burn any tissue when active. So in order to meet this marker requirement, we created a design input that the implant must not reach temperatures above 38.5 in situ, which is 1.5 degrees Celsius above body temperature at homeostasis. So in designing the product, we decided to come up with a solution that's optoelectronic in nature by leveraging the magnetoelectric effect. This is due to its high power density and miniaturization potential, and magnetism's unmatched transmissivity through biological tissue when compared to technologies like ultrasound. The way the system works is that we have external input coils of AC and DC varieties that resonate at a certain frequency and resonate with a magnetostrictive foil that is bonded to a piezoelectric fiber. When this magnetostrictive foil resonates, it will provide a mechanical input on the piezoelectric fiber, producing an AC voltage that is then put through an on-chip rectifier microelectronic circuit, whose load is a LED of a designed wavelength. This will then provide a DC current to light it up and deliver a light dose to the retina. I'll now hand it off to Christina, who will go over how we verified these 3 design inputs.
So corresponding with our 3 design inputs, we had 3 verification tests. We had temperature, transmissivity, and spectral characterization. The most important of this verification test was the transmissivity. So a Gauss meter was used to measure the DC field based on the distance of the magnet, and the photometer was used to capture the amount of watts, which was then converted to number of photons emitted by the LED based on a corresponding DC field. As you can see, there is an optimum position, an optimum DC field for maximum photons. However, the maximum amount of photons emitted is way too high for our purpose. Therefore, we'll be sticking with using the left-hand tail of the curve, which has a lower DC field. Therefore, it allows for the preservation of the circuit because it consumes less power. The second test was spectral characterization. So a spectrometer was used as well as with an integrating sphere. 2 peaks were seen. This was expected since it's a cyan light, and it therefore composed of both green and blue light. Finally, for the temperature test, a thermocouple was used to measure the temperature of meat by itself, tissue, and the temperature of porcine tissue with the LED. As you can see, both graphs behave similarly, which could indicate that the LED had no effect on the temperature of the tissue. However, what was unexpected was the decrease in temperature, and this can be further redesigned by keeping the tissue at body temperature to better imitate physiological conditions. I'll now pass it over to Jeffy to discuss implementation and future work.
Thank you, Christina. For implementation and the fabrication of this device, we have considered 3 steps, including power source development, rectifier PCB development, and bonding of components. For a location where this device will be implanted is going to be the posterior segment of the eye, which is in close proximity to the retina, where the illumination will take place. So this device will be activated during the patient's sleep to increase the oxygen consumption in the retinal red cells. So when the retinal hypoxia is decreasing, so suppressing the development of diabetic retinopathy, that's when the wards are adapted to the light during the patient's rest. So this device, compared to current modalities, will avoid future treatments and expenses. And for future works, this is a wireless multiferic power delivery that has many great applications. So what we want to consider in the future are development of fixation features, further miniaturization, and magnetic coil refinement. And also we want to reach out to ophthalmologists for further development and also surgical procedures. Thank you for watching our poster presentation. Please feel free to reach out if you have any questions. Thank you.